Hey, Comp 1113, here we are, Unit 8, continuing on with matrices. We'll do another example of Gauss-Jordan elimination. Then we'll talk about the cases where it can fail. And then we'll work on some basic matrix operations. So let's get right to it. Here's a little example of an augmented matrix where we have three equations with three unknowns. The columns are listed as, instead of X, Y, Z, it looks like we have A, B, C in the PowerPoint slide. I thought we'd go off and do this one by hand. You'll see the numbers are a little bit uglier than maybe in the previous example. We'll see what kind of, trouble we'll get into with the fractions. So I already copied that over to my OneNote. And I actually wrote it with X, Y, and Z, but it doesn't matter. The same three equations with the three unknowns are X, Y, and Z. Here's the matrix that was showing in the PowerPoint. And now let's do our Gauss-Jordan elimination to this, trying to solve for X, Y, and Z. Step one is to try to get a 1 in the upper left corner. To get that, we're just going to divide row 1 by 2. So we'll get 1, 1/2, negative 1/2, and 7. And we'll leave the other rows alone for this step. I try not to do too many steps in each matrix. In the PowerPoint, I tend to do maybe too many steps per rewrite of the matrix, just to save space in the PowerPoint slides. Personally, I'd rather maybe write more than what's actually shown there. If we want to write what we did 1/2 times row number 1. The next step is to use that 1 or that pivot to eliminate the other values in that column. So we have a 1 here, and we'll use it to eliminate these two 2's beneath it. After just giving the little speech about not doing too many steps in one matrix, I will do those 2 rows at one time. So to eliminate the 2 in row 2, I'm just going to have to multiply row 1 by negative 2. So it'll be negative 2 row 1's plus row 2. So minus 2 row 1 plus row 2 old gives us row 2 new. And we'll do the same thing actually to get rid of the 2 beneath it. It'll be minus 2 row 1, but we'll be adding it to row 3, and we'll put our answer right here. So here we go. I'll just write my little cheat note here. I'm going to be multiplying by negative 2. So it'll be negative 2 times 1, which is negative 2 plus 2 gives us 0. And we do that for the whole row. So minus 2 times 1/2 is negative 1, and negative 1 plus 1 is 0. That's interesting. Negative 2 times negative 1/2 is positive 1, and 1 plus negative 6 is minus 5. And then we just keep going. We're over to the 7 now. Minus 2 times 7 is negative 14. And then we're going to add that to 43 over 2. So that's negative 28 plus 43 over 2, which ends up being 15 over 2. In the PowerPoint slide, I believe I had a decimal value there. When I'm doing these by hand, I prefer to work with the fractions, primarily because sometimes these fractions end up being something that you'd have to round. And if you round in the process, you've then introduced error. But if you work with the exact fractions, then you've never done any rounding and you get the exact answer when you get to the end. But you could use your calculator in this case because 15 halves is 7.5, right? We could write that exactly. It's just like when you have numbers like 1/3, you don't want to write just 0.33, for example, because that would mess up your answer at the end. Yeah, let's do the last row here. So we're going to use -2 again, multiplying it by row 1, and then we're adding it to row 3. So -2 times 1 is -2, and -2 plus 2 is 0 as desired. -2 times 1/2 is -1 plus 5 is 4. -2 times -1/2 is +1, plus -3 is -2. And then -2 times 7 is -14, and -14 plus 47 is 33. Again, I leave this space over on the right side in case any of that math gets too hard. I'm not sure. It was 2 times 7 plus 47 is -14 plus 47, which ends up being 47 minus 14, which is 33. We're looking pretty good now. We have the first column set up, but our next step is to get a 1 here in the center. And you can't really turn a 0 into a 1. I mean, we could try to combine a row with that row, but in the process, we'll probably mess up our 0. So I'm thinking this is a good opportunity to just swap two equations around. I'm going to put 0, 4, minus 2, 33, row 3 in the middle. And then I'll put the 0, 0, minus 5, 15 over 2 as the last row. That's a valid operation. I just switched the order of the equations. The middle row is an equation and the last row is an equation. It doesn't matter what order you write the equations in. And the first row, let's just leave that alone. For notation, sometimes we'll write row 2 was swapped with row 3. A double arrow meaning they're swapping. Now we can try to get a 1 in that middle position by dividing that row by 4 or by multiplying it by 1/4. I'll leave the other stuff alone. So I'll have -2 over 4, which is -1/2, and 33 over 4. I may regret that I, didn't leave this in fourths, that I reduced that fraction, but we'll see. So that was 1/4 times row number 2. Be careful each time you recopy so you don't lose the sign, or sometimes my numbers my 9s start to look like 7s. So just be careful as you go. Take your time with these, because if you make a mistake, it's really hard to find it, and you basically have to do the whole thing over again. The next step is to use the pivot to clear out the rest of the elements in that column. Well, we're in good shape. We already have a 0 below that pivot. So the only one we have to worry about is clearing out this 1/2, which is above the pivot. So I'm going to leave row number 2 alone. I'm going to leave row number 3 alone because it already has a 0 right here. So we actually saved ourselves a little bit of work. And now we're going to try to go after this 1/2 here. To get rid of that, it'll be -1/2 times row 2, and then we'll add that back to row 1. So I put my little note out here. I'm going to multiply by -1/2. So -1/2 times 0 is 0, and then I add that to 1, and this remains a 1. Again, doing it in the order that I'm doing it in helps make sure I don't mess any of the previous things up that I've already, established. Negative a half times 1 is negative a half, plus a half is 0. Negative a half times negative a half is positive 1/4, and 1/4 plus negative 1/2 is equal to negative 1/4. And now the hard one, maybe negative a half times 33 over 4. So negative a half times 33 over 4, and then we have to add 7, which is negative 33 eighths plus 56 eighths, which ends up being 23 over 8. And now we continue on. The next step, you can see that we have this column the way we want it. We're down to converting this minus 5 into a 1 to create a pivot for this column. We can do that pretty easily. Just divide by minus 5. So 0, 0, 1. 15 over 2 divided by negative 5. Or maybe write it as maybe easier to imagine you're doing negative 1/5 times 15 over 2. And then you can do nice cancellation and get negative 3 over 2. And I'm going to leave the rest alone just for this step. There. Now we use our pivot here to clear out what's above it. Technically, we wouldn't have to. We currently know what z equals. Z is negative 1 or negative 3/2. And then we could substitute it in the previous equation and to figure out what y is, and then plug in z and y into the first equation to figure out what x is. That's called back substitution. But it's more efficient if we just finish this whole thing off. So let's wipe out these two spots. So I'm going to rewrite row 3 because it's done. And now we're going to try to eliminate this negative half and negative a quarter. To eliminate a negative half, I'll multiply the third row by positive a half and then add it to row 2. And to eliminate the negative a quarter, I'll multiply by positive a quarter and then add it to that row, which is row 1. Let's do the middle one first. I'll put my little note out there. I'm going to multiply by a half. So a half times 0 is 0, and 0 plus 0 is still 0. A half times 0 is 0, and 0 plus 1 is still 1. A half times 1 is a half, and a half plus negative a half is 0. I probably didn't really need to do all that. I think we knew that's what was going to happen. And now the hard one. We have a half times negative 3/2, and then we're adding that to 32 over 4. So we have negative 3 over 4 plus 32 over 4. Is it 32? Oh, it was 33. I copied it wrong. I had it correct here, and then it fell apart. Luckily, it didn't. We weren't using it during these steps, so I can quickly just update that if you're following along. I'll just use a different color here. Sorry about that. This is 33 over 4. 33 over 4. And this is Now I'm multiplying by 33 over 4. See how easy it is to make a mistake in these guys? So I just want to, if your spidey sense starts tingling, go back and take a look, make sure you didn't recopy something wrong. Now that I'm doing this math, it was positive a half times negative 3 halves, and then I'm adding it to 33 over 4, and we have negative 3/4 plus 33 over 4, which ends up being 30 over 4. Maybe we'd be better off to write 15 over 2 right here. Whew. I'm glad we caught that error. I didn't want to have to redo this whole video. Next, we're going to try to work on the first row, meaning we're trying to eliminate this negative a quarter, and to do that, we're going to multiply by positive a quarter. So a quarter times 0 is 0, plus 1 is 1. A quarter times 0 is 0, and 0 plus 0 is 0. A quarter times 1 is a quarter, and a quarter plus a negative a quarter is 0. Now we can do the fractions. We have 1/4 times negative 3 halves, and then we're adding 23 over 8. So that's negative 3/8 plus 23 over 8, which must be 20 over 8, which simplifies a bit. That is 5 over 2. We did it, hopefully. We now have the augmented matrix in the form that shows us what each variable will be. The first row tells us x. X is 5 halves. The second row tells us y. Y is 15 over 2. And the third row tells us z. Z is negative 3 over 2. We should check it, especially after that little blunder I made. So let's plug these guys back into the original equations. I think I have them written up here, so I'm just going to sneak them in up here. Our answer was x was 5 halves, y was 15 halves, and z was negative 3 halves. Now you have your calculator, so that would probably, on a test or something, you could answer this or check this quicker, right? I'm just going to plug these values into all three equations. So 2 times 5 halves plus 15 halves minus negative 3 halves. And hopefully this ends up equaling 14 because I'm using the first equation. So we get 5 plus 15 over 2 plus 3 over 2. So 5 plus 18 over 2. So 5 plus 9 is 14. And the first equation checks out. We really should check all of the equations to be sure. So the second equation is 2 times 5 halves plus 15 over 2 minus 6 times negative 3 halves. And this is supposed to equal 43 over 3. Let's see what happens. We get 5 plus 15 over 2 plus 18 over 2, which is 9. I guess we need to put this in common denominator here. So we have 14 over 2 plus 15 over 2. Oh no, that doesn't seem right. We're ending up with, let's see, am I not right here? 14 plus 15 over 2, which is 28 plus 15 over 2, which ends up being 43 over 2. Did I write that? Oh, I didn't even write down the question right. Should have been a 2. It was from the slide, it was over 2. So thank goodness. So there's another mistake. I couldn't even copy the lecture slide correctly. I had a student email me the other day asking me to check his work on one of these, and I couldn't find anything wrong with it. It was perfect. And the only thing that was wrong was he copied the first equation wrong. Like he forgot a minus sign. So yeah, here's me. Actually, I didn't even copy this from the other slide. I was just trying to remember it. Last equation. Oh, geez, let's check it. 2 times 5 over 2 plus 5 times 15 over 2 minus 3 times z, which is negative 3 over 2. And that's supposed to equal 47 if we're doing things right here. Let's see. It might be easier to leave this all in halves. Let's do that. Let's say it's 10 over 2 plus 15 times 5 is 75 over 2. And then plus 9 over 2 gets us to 85, 94 over 2. And what are we aiming for? Is that 47? Sure it is. Whew. Well, it all checked out. These things are tricky. It takes practice in order to get them right. The nice thing about them, though, is that when you get it wrong, you know you're wrong. So it's just persistence, going back, heading back through them. Oftentimes, if I make a mistake, a lot of times I just scribble it out, or I start with a whole fresh sheet of paper and start over, just for fear of it. It's really hard to see a little mistake where you forget a sign, or I just wrote down the question, or I just copied the number wrong. So little things like that are hard to spot, but you can check your work at the end. If you're wrong, you know you're wrong. So on a homework assignment, there's no excuse for getting it wrong. On an exam, yeah, there's excuses for getting it wrong because of the time pressure. I often would save a question like this for later in the exam, just because I know it's kind of a time sink. Let's head back over to the PowerPoint. The PowerPoint traces through what we did. It's using A, B, and C for the letters. So you can click through this at your own pace, but you'll see that the numbers are matching, hopefully, what we did as we went along. I even had to do the same trick of where we swapped 2 rows around. You can see I didn't use very many matrices in the PowerPoint slide, and I also used decimal along the way because it's easier to type. And they were all exact values. Like instead of using -1/2, putting -0.5 works just as well. And if you have your calculator with you, there's nothing wrong with this, because dealing with these 2.875 is no big deal with your calculator. So hopefully this ends up equaling what we ended up getting. I believe it is. Yeah, we had X, Y, and Z equaling these values, so they match. Sometimes when you're solving these things, though, you don't get an answer, or you get infinitely many answers. So we're going to have to talk about those now. Those situations are called when your equations are called linearly dependent or inconsistent. So we'll have a couple new terms to define there. the cases where you have no solution and infinitely many solutions. Here's a little example. I'm back to two equations, two unknowns. These are just two lines. You could graph them, see what they look like. If we try to do our Gauss-Jordan method on this, we put the two equations into our augmented matrix. You get a 1 in the upper left corner. It's already there. Yay. So we just have a few more to go. So we'll try to eliminate this 2 using the 1. So we'll multiply row number 1 by -2 and then add it to row 2. And something weird happens. You end up with a row of all zeros. Now, the next step of the process is to turn this 0 into a 1, but you can't. I mean, you can, but it will turn this 0 into something other than 0. So what's going on here? Well, if you rewrite the equations for these, the first equation is 1x plus 2y equals 5, but the second equation is 0x plus 0y equals 0, which is a statement that is always true, no matter what. We're saying now that the second equation is dependent upon the first equation. So basically, no matter what you use in this, it's true. Which means that there's going to be more than one answer to this. It means that there's actually going to be an infinite number of answers. If you look closer at these two lines, at the equations as you see them, you'll notice that one is just a multiple of the other. So they're the same line. The first line and the second line are the same. They have the same slope. So because they're the same line, there's going to be an infinite number of points where they are the same. They don't just cross at one spot. The other place that things can go wrong is when you have inconsistent equations. So here are two equations. We'll just march along doing our Gaussian elimination as we normally would. Put them in the augmented matrix. We already have a 1 in this pivot spot. We're going to eliminate this 2. To eliminate it, we're going to multiply row number 1 by -2 and add it to row 2. When you do that, something weird happens as well. -2 times 1 plus 2 is 0. -2 times 2 is -4 plus 4 is 0. And -2 times 5 is -10 plus 9 is just -1. Now check out the second equation here. Again, we don't have a 1 in the pivot spot. And we can't really get one there without making this first spot a 1. So think about what this equation means. Like if we write the second equation out, we end up with 0x plus 0y equals -1, which basically says that 0 equals -1. And that's impossible. There are no x and y that could make 0 equal -1, which means that there's no solution for this system of equations. And we call this inconsistent. Basically, you have two lines here that have the same slope, but different y-intercept. So they never cross. So if you have two lines that never cross, then there's no solution. So the dependent case is when the two lines are the same line, and the inconsistent case is when the two lines are parallel to one another and therefore never cross. Do you need to know that when you look at the equations? No. You can just go through your Gaussian elimination, and when you run into these situations, then you can interpret them. 0x plus 0y equaling some number is wrong. It's inconsistent. So this will pop up in the three equations with three unknowns. It's harder to, visualize that because, you're in 3D space and you're talking about planes. And then once you go to four equations with four unknowns, it becomes almost impossible to try to imagine, things that are parallel, for example. So uh, even without being able to see it or imagine it, it just will be something we can see in the augmented matrix. So sometimes we're going to have answers like there is no solution, like this equation. And in the previous example, there were infinitely many solutions because they were the same line. So hopefully you're okay with, I'm going to use the term dependent system and inconsistent system. So make sure you know the difference between those two words. One means no solution and the other one means infinitely many. Now we've been using matrices. Now it's time to maybe, give some definitions of these things and do some other operations besides just Gauss-Jordan operations. Here's a matrix A. We refer to it as having dimension. There are rows and columns. We can represent each element of the array by its row and column position. So this position in the matrix is row 1, column 1. And so we'll write a subscript like this. The next element of the array is row 1, column 2, row 1, column 3, row 1, column 4. And then the next row is row 2, so row 2, column 1. This is backwards from spreadsheets. When you're using a spreadsheet, you reference the addresses or the cells by their column letter and then their row number. But in math, matrices are always listed as row by column. We often use uppercase letters for a matrix that's not just a row or a column. And we often have them boldface for notation. This matrix here has 3 rows and 4 columns, so its dimension is a 3 by 4 matrix. So matrix A is 3 by 4, and these are elements of matrix A. We can do some operations to these things. We can actually add two matrices together. That is, if they have the right dimensions. Here's an example where I have a matrix that is 2 rows by 2 columns, and I'm trying to add it to a matrix that is 3 rows by 2 columns. Well, I can't add those because they have a dimension mismatch. But I can add and subtract matrices that do have the same dimension. Here are two. I have a matrix that is 3 by 2 and another matrix that is 3 by 2, and I can just add these together. And to do that, I just add element by element. So row 1, column 1 in the first matrix is 3, and row 1, column 1 in the second matrix is 1. I add these two elements together, and I put the result in row 1, column 1. So the 3 here plus the 1 here gives me a 4 there. So matrix addition is super intuitive and easy. Subtraction works the exact same way. If I did this first matrix minus the second matrix, that first element would just be 3 minus 1, and I'd put a 2 here. So you should be thrilled if on the final exam you get a question where it says, add the following matrices together. You'd be really happy if I gave you the one up above, because then the answer would be, you can't do it. And if I asked why, you could then say, because the dimensions don't match. We can multiply by a constant. So here's a matrix. It's a little one. It's a column matrix. It has 2 rows and only 1 column. Sometimes we call these things vectors. I can multiply this matrix or vector by a constant 2. And to do that, you just multiply it by each element in the matrix. So this is maybe useful, maybe more useful the other way. We can also factor. So if you have a matrix, with the first element 6 and the second element 10, you could factor something common out of those two, like the 2, and it might help you simplify. Here's a 2 by 2 matrix. I can multiply it by -3. And to do that, just multiply -3 times each element of the matrix. Pretty easy. And again, you can factor. If you had a matrix here on the right, and you notice that -3 was common to all of them, you could factor that out. And maybe it would be nicer to write this way. And here's me just talking about factoring. Here's a matrix that has, common multiple of 2. So I factored 2 out of each element, and I'm left with this. Multiplying matrices, that's a little trickier. It's basically dot products or vector multiplication. We have to be careful about dimensions. They don't have to necessarily be the same. It turns out that the number of columns of the first matrix has to equal the number of rows of the second one. Hopefully I said that right. Each element of the resulting matrix is a product of one of the rows of the first and the columns of the second. Yeah, I did do that right. So to do this, I take a row of the first matrix and I multiply it by a column of the second matrix. So that's why the number of columns of this one has to equal the number of rows of this one. To do that, I'll take row 1 times column 1. And to do that, I'll take 1 times 3, and then I'll add 4 times 5. Maybe I should write that. Basically, I'm taking this one, and I'm multiplying it by 3. And I'm taking this 4 and multiplying it by 5. And I'm adding those two products together. So it's 1 times 3 plus 4 times 5. And that's how the 23 comes up. And because I multiplied row 1 by column 1, my answer will be in row 1, column 1. Next, I'm going to take row 2 and multiply it by column 1. To do that, I'm going to multiply 3 times 3 and 2 times 5 and add them together. So 3 times 3 plus 2 times 5 is 9 plus 10, which is the 19. And I used row number 2 with column number 1, and that's the position of my answer. So it's kind of weird that your dimension here, it doesn't get bigger necessarily. I'm going to erase all this stuff. There's a nice way to check to see if you can do the multiplication using the dimensions of those matrices. The first matrix is a 2 by 2 matrix, and the second matrix is a 2 by 1 matrix. 2 rows, 2 columns, 2 rows, 1 column. Well, to check to see if you can do it at all, these two numbers have to match. If they do, cool, you're able to do it. And your answer ends up being the dimension of the other two values. Our final answer here is 2 by 1. So there are going to be times when you can't multiply matrices. You have to first establish this. Just like there are times when you can't add them. If their dimensions don't match, you can't add. For multiplication, the overall dimensions don't have to be the same. Just the rows of the left one have to equal the columns of the right one. And here's me just saying the same stuff I just scribbled. When you're multiplying matrices, yeah, this is an important little tidbit. The order matters, which is something that has never been true for you probably in your whole math career. Multiplication in Boolean algebra, it didn't matter if you said A and B or if you said B and A. When you multiply 2 times 3, it's the same as 3 times 2. But when you multiply two matrices, the order will matter. In a case like this example, if we tried to switch these two matrices around, it's not even possible to do it. Here's an example. I have a matrix that is 3 rows by 2 columns, and the second matrix is 2 rows by 4 columns. Can we do that? 3 by 2, and the second one is 2 by 4. So it's going to work out. And our answer ends up being listed here. It's a 3 by 4. To get this number 17, I'm doing row 1 times column 1, which is 1 times 2 plus 3 times 5. It's kind of fun. So 2 plus 15 is 17. Say we wanted to get this, say 86. Where did that come from? Well, figure out what position we're in. We're in row 3, column 2. So I'm going to multiply row 3 times column 2, and that should get me this 86. Let's check it. 4 times 8 plus 6 times 9 is 32 plus 54, which hopefully ends up being 86. So it's a little tedious to do all these multiplications, but it can be done. And especially if the numbers are nice, like, integers like this. So I'll let the PowerPoint fill this, probably the same stuff in. Here's me checking the dimensions. Here's me knowing what the answer is going to look like. And then the multiplication is, well, just do it systematically. Row 1, column 1, row 1, column 2, row 1, column 3, row 1, column 4. Fill in row 1, and then go row 2, column 1, row 2, column 2, row 2, column 3, row 2, column 4, etc. until you get the whole thing done. It takes a little time, but it's not too bad. In computer graphics, this is basically what's happening during all animations or resizing, or basically every change to your screen is a bunch of matrix multiplication. So it's one of the reasons why it's hard to have fast computer graphics, because it's very computational. You have to do a lot of multiplications in order to do, each frame as you make changes to the screen. Speaking of computer graphics, I have a little example here. Suppose I have this three-dimensional little tetrahedron, I guess I've drawn here. It doesn't look three-dimensional on your screen probably. I have a point here that is x is 0, y is 0, and z is 0. So imagine that the z-axis is, coming out of your screen right at you. This point is just sticking out of your screen, and it's also going behind your screen. So that's your z-axis. I have another point at 1, 0, 0, so that's this point. So here are the first 2 points, and I put them in a matrix. I have an X column, a Y column, and a Z column. And then row 1 is point number 1. Row number 2 is point number 2. Row number 3 is point number 3, which is, where is it? This point. Here's point 3. All of those had a Z of 0, so they're flat on your screen. But then there's a fourth point here that is at 0.5, has a Y value of 0.2887, but then its Z value is negative 0.8. So think of it as behind your computer monitor by 0.8 units. So you basically have this triangular, prism going on. We can then manipulate. We now have basically a 3D object, and we could change it. We can rotate the thing, we could skew it, resize it, all kinds of different operations. And to do that, we can just figure out a whole new set of points. We're just introducing this in this course. You talk about computer graphics in other courses in the program. So I'm not making you memorize this or anything. I'll give you a little homework assignment. You'll mess around with these things a bit. But I'm not going to require you to, memorize these operations really. I just put in some crude computer graphics here. This is the kind of stuff that maybe we'd be capable of at this point. Here are the matrices that are used to do rotations of points. These things are just well known. If you're rotating about the x-axis, you multiply your set of points by this rotation matrix. And the rotation depends on whatever angle you want to use. So if you want to rotate by, 60 degrees, you put in 60 degrees for theta, and then you multiply that by your matrix that contains your data points. Or if you want to rotate around y, you use this matrix. If you want to rotate around the z-axis, you use this third matrix. So it does require, a little bit of trigonometry. When you're programming, make sure that you convert your angles to radians. I believe most programming languages have a math library, and those built-in functions for sines and cosines, I'm pretty sure require that you use your angles in radians rather than degrees. So we'll do our quick little example of rotating around the z-axis by 45 degrees. We had our matrix here of points. Remember, the first point was 0, 0, 0. The next point was 1, 0, 0. The next point was half, 0.8660, and then the fourth point. If we want to rotate that around the z-axis, we would just multiply by our rotation matrix, and I just substituted in pi over 4, which is 45 degrees. You do this multiplication just like you would. You take 0 times this one, and it's a row by a column. So then 0 by that one, and 0 times that one, and you get your answer. Here it is. I'm multiplying 4 by 3 matrix times a 3 by 3 matrix, and I end up with a 4 by 3 matrix. Now we have a new set of points that we can plot. And what we get will be our original points all rotated around the z-axis, which is the axis that's sticking out of your screen, by 45 degrees. So here's what it would look like when we're done. And I think I put it in here to remind us. Here's what it looked like when we started. Here is the original matrix P. This matrix defined this figure. and then we rotated it 45 degrees. So you notice that this point here didn't move at all, because that's where the z-axis is pointing out of the screen. So if you're rotating around that, that point just rotated right on the spot. But the other points here rotated 45 degrees counterclockwise. So this value got moved over to here, and the center value moved up to here, and this value moves up to here somewhere. This is the end result. That's kind of neat. So if you're trying to do this in an animated way, you'd set some sort of loop or something where you just gradually increment the angle. Rotate by 1 degree, then 2 degree, then 3 degree, then 4 degree, and just keep refreshing the screen each time you got a new set of points, and then you would watch this figure actually, be animated as it rotates from the original position to the new position. So that's just the very, bare basics of this whole idea of computer graphics. But it's pretty cool that it really just comes down to defining your points in a matrix form and then multiplying two matrices together to do transformations. Basically, that's the key thing we needed to learn in this course, was basically how to multiply two matrices together, which is one of the easiest things that we do. Multiplying by, sines and cosines is a little ugly, but we can manage it. I'll try to give you nice angles, but you all have your calculators. You just need a scientific calculator, and make sure you have radian mode in order to do these, computations. So that's our application of, basic application to computer graphics. In the next unit, or continuing on in this unit, we'll learn a couple more operations, or at least one more. We'll learn how to do the determinant, and we're also going to learn how to find the inverse of a matrix. But in the next one, we'll just focus on determinants. So hopefully you'll all stick around for that, and I will see you there. Take care and have a good day.